This is our generic cloud. We're going to have it inside tropical cyclones. It could be a cloud anywhere. And this is the entire moist and dynamic energy that, that a parcel can hold. So if you can move on one more. Nothing happened. Oh, there it is. So basically we've got sensible and latent energy being advected in the trade zone into here. There's a little bit comes out from underneath the storm as well, out of evaporation, but the bulk of it is advected into the region. It then goes up, hit one more.
Now you can do it again.
Okay, thank you. It then goes up and a lot of people think, oh, latent heat just warms the atmosphere, but latent heat does not warm the atmosphere at all, except for a little bit of local subsidence in the vicinity of the storm, which dries it out and actually warms up a little bit. There is essentially no heating of the atmosphere by latent heat. What happens is, as you come into this cloud and you start rising, you get condensation. The condensation warms the parcel. The parcel starts to rise, which means that energy goes to half mv squared. The mv squared moves the parcel up, and that energy goes to GZ. And by the time you've done all of that process, what comes in the bottom is sensible and latent energy, and what goes out the top is potential energy. Now, there's a little bit of sensible and latent energy in that being advected out the top. There's a bit of kinetic energy coming out the top as well. There's actually, there's even a cooling up in this area because you get a bit of evaporation of cloud and things like that, but they're all extremely small compared to that term there. And that's the only one that's important to the energy budget of importance. And I think I'd be able to show you that. At the same time as all this is happening, the atmosphere out here somewhere away from this particular thunderstorm or tropical cyclone is radiatively cooling at about 1 or 2 degrees C per day, every day. And that area is clear. So just to emphasize, oh, sorry, sorry, this is the most important point, and the cooling is actually balanced by subsidence, where GZ gets handed back to CP2 by the compressional warming of the atmosphere, of the parcel as it comes down. So the fact that this term here in particular doesn't respond to anything except being lifted up so it can actually drop its rain out. And the fact that this term here does not respond to radiation and various other things means that's why you can actually transfer energy around over extremely large spatial scales and time scales for that matter. So when we come back and look at this rather simplistic viewpoint, none of it actually ever happens. There is evapotranspiration. It is actually where the evapotranspiration is not where the upward motion's occurring. There is latent heat. It's not like you get suddenly all this latent heat then warms the atmosphere or things like that. There is an entire dynamic process that's going on that maintains this process, that maintains this entire system. So let's get, after that sort of starting point, let's get to contribution by tropical cyclones. And what I'm going to show here, or what I'm going to discuss, is the potential contribution from vertical energy transfer and conversion in tropical cyclones, the major characteristics which influence that energy transfer, where the energy goes, and then we'll finish up this bit of a section with the issues with spatial and temporal transience. And I do have to say, this is an important one. It sort of looks obvious when you've gone through the research that we've done, but when you start off, this actually stopped me even thinking about this being a possibility for a long time, because there's a tropical cyclone, the cooling's occurring here. How in hell's name is that affecting that? The tropical cyclone only lasts for a week, maybe 2 weeks. This happens all year. How can the tropical cyclone affect that? It requires this long timescale process to be there. So we're going to look at the energy balance in tropical cyclones. We just basically draw a box around a tropical cyclone in the reanalysis system. You've then got E in, which is the horizontal fluxes. You can read the rest of it. We've got E out, which is the horizontal fluxes out. There's a little bit out the top, but it's essentially zero. And then there's a gain. Tropical cyclone might be intensifying or whatever. This is actually quite small. It's these two that are the two big turns, and they roughly balance. They're balanced within the accuracy of the calculations that we're making, for sure. yeah, Microsoft. What more can I say?
Great. How you doing?
Hey, matey, how you doing?
Good. Could you comment on, you have the diagram there saying, well, look, it's air parcels going up and, that's increasing its potential energy. But, the air that's replacing is going to have a very similar temperature to the air that's coming up because of the latent heat. So
there is for the purpose of this discussion, there's no exchange of thermal energy.
Right.
But the point about the potential energy, and hang with me for a little bit because I'll be showing this as we go. What you've got out in the clear area is air subsiding. You're giving up potential energy from the atmosphere. You've got to replace it from somewhere, and here's where it gets replaced from. So forget local. From here on in, forget local completely. It's got nothing to do with what's happening local. Because there's all ups and downs in the tropical cyclone as well, and we're not averaging, we're actually smoothing them all out because of the way we do the budget. So we're getting rid of all of that local ups and downs. It's just noise as far as this discussion is concerned. It's looking good, but I'm not going to touch anything. Keep going. Okay, so that was where we're at. You've just heard that, so give me one more, please.
I think it doesn't matter whether you go with your, use it.
I'll use this one, okay. So just to emphasize, this is how we do the calculation. You've already seen the equation at the top. It's now in the form that you actually use to do the calculation. As I said before, we account for frozen particles by using the technique of breadth in that hole. It's not an insignificant part. You can't, well, you can, but you're leaving that out actually makes a difference. And then we've got the total energy balance in the whole system obviously has to approximate to zero. And
I think we just do this because the formulas are so complex so that we have a little bit of discussion time.
Yeah, so one thing that I do remember this happening some time ago. Are you using my stick, or you've actually, no, you downloaded it in there? Okay. Trying. I'm getting too old to remember what I actually wrote down on the slides, but let's keep going. So in the actual tropical cyclone, what we've done is we've got a reanalysis. I'll show you the data sets that we're using in a second. We've got a reanalysis, which has obviously got data on levels, and it's got a grid spacing. So we basically go in and we calculate the energy transfers through each of those grids, etc., into, out, and also the energy exchange in the grid, which then obviously comes out at some point because you've exchanged it and then given it away to somewhere else. We do that around the whole tropical cyclone and through the whole vertical part of the atmosphere. And at the end of all this, we've got a certain amount of energy coming out the top. And then we're going to start following what happens to that energy as we go out the top. Keep going, one more. Okay, give me one more. Right, so we're now back up to date. What I'm going to do is I've got ERA interim. These are the databases we've used. JRA, that's the Japanese one. The WRF operational forecasts over the period you see there at 4 kilometres. The other two are at about 70 kilometres. And the 4 kilometre climate run that we did several years ago now, which has 20 tropical cyclones in it. I'm mostly going to show ERA interim, but we've done all of them. And I'm just simply letting you know that we've done the comparisons and everything else, and I won't bore you with the details, but if you want, I can show them to you later, or alternatively, you can wait till the paper comes out and it'll be in the appendix. Now, we've got a tropical cyclone and we've put a box around it. How did he decide the size of the box? Well, we actually thought about it for a while and we came up with all sorts of sexy ways of doing it. We said, well, that's a bit bloody silly. Let's just simply calculate it and see what it matters. So this is the way we did it. We just simply put boxes of different sizes, 160 kilometres on the side, 480 kilometres on the side, 1,000 kilometres on the side, around a few tropical cyclones in the ERA interim. And basically you can see once you get out to about 600 to 1,000 kilometers, everything is converging. So we ended up choosing 900 kilometers as the box size we'd put. And that's there. If it's a small cyclone, it's the same box. If it's a big cyclone, it's the same box. We're not getting into that game. It shouldn't matter, except if it's a really big cyclone, then obviously we're cutting it off at part of the cyclone, which means that the calculations we made will be conservative, not in the other direction. We calculate the, well, you can see how we calculate it over there in the sense of I've already described it in the previous slide. Right, so just to give you the answer, before we get into the details, for vertical energy transport for all of the tropical cyclones around the world is 5,600. If you compare that to the subtropical cooling, it's about 30% for the global. If you just take the summer hemisphere, in other words, it's 75%. If you take only the summer subsiding Hadley circulation, which is a bit that's going north and subsiding, it's 43%. And if you sort of add all those up and divide by n, you end up with something like 50%, maybe 40, maybe 60, given the error bars, but somewhere around 50% of the energy that goes up in tropical cyclones the energy that goes up in tropical cyclones would actually supply about 50% of the global energy budget deficit. So it's a big number. And there's lots of errors in the analyses, as you'll see. There's lots of other things. So this is all a rubbery figure, but it's somewhere up in that sort of spatial, that sort of amplitude scale. Here is two examples. This is just simply calculating the poleward energy transport percentage, but if you take the bit up the top, that's the bit that stays in the tropics, going from 4 degrees up to 50 degrees. From the tropical cyclones, the blue is ERA interim, the JRA is the red one, is the Japanese one, and the error bars are actually the spread across the system. And basically, you can see in the tropics, most of the energy stays in the tropics. Let's say around 20 to 30% goes off into the Hadley circulation. The rest stays in the tropics. Once you get beyond about 30, maybe 35 degrees, I don't care which one you pick, then about 40% of the energy that's going up in those tropical cyclones is actually heading into and is going into the Hadley circulation. So we're actually contributing to both. The main point of this thing is to say there is a lot of energy going sideways as well as energy going polewards. And I thought when I first put the process together, to be quite honest, I thought the energy going sideways is going to be so bloody small it won't matter. So I thought, okay, we'll have to realize that all it's doing is feeding the Hadley circulation. It's not true. It actually feeds the tropics better than the Hadley circulation in that context. This is just how it looks if you just simply calculate the numbers around the globe. The top one is ERA interim, the bottom one is JRA, and you can see there's significant differences. The patterns are about right. What we have over here is the WRF operational forecasts. The cutoffs is because that's as far as the operational forecast basically provide us information. This is on a small grid sitting inside a bigger grid. So you have to be a little bit careful with this, but we wanted to do it as a comparison. And the main thing is it's got about the same sort of patterns as if you look at the Atlantic over here, the Atlantic and the Pacific, as you get in the Atlantic and Pacific, but the numbers are much larger. And I'm going to stick my neck out and say, I think that is partly because of the fact that WRF is on a grid, on an internal grid, and is therefore being driven by what it can actually hand to the outside world. I think it's also partly because it's 4 kilometers, therefore it's seeing the interior parts of the cyclone, and the moist static energy at the surface at, say, in a hurricane force system, the moist static energy at the surface is about 30% higher inside at the radius of maximum winds than it is outside the cyclone, same level. The reason for that is the pressure's gone down, the temperature and the humidity have stayed the same or even gone up a little bit. So if you think theta E is the easy way of thinking about it, you've actually changed the you've changed the moist static energy substantially. Again, it's not new information. This has been around for years. So, what is it that determines the vertical energy flux? In other words, this is what we saw. What were the things that were sensitive, what was it that actually provided answers? And originally, my original hypothesis was it was the intense cyclones that were providing most of it, and the weaker cyclones were providing nowhere near as much. And as you can see, at least in ERA interim, that was wrong. Basically, this is tropical storms, less than hurricane force. This is hurricane force, and this is major hurricanes. And I use the US system everywhere. I can't be bothered with trying to reinterpret for every region I go into. And you can see there is a change. You go from 4.6 to 4.7 to 5.2. And so basically, there is an increase due to intensity, which is due entirely or almost entirely to that additional static energy that's available. But it's not enough to say that, hey, tropical cyclone intensity is a big number. It is underestimated to some extent because of the lack of resolution in the core. So there'll be some number bigger than that, but I suspect it'll never be more than about a 15% increase that we observe as you go to more intense cyclones. Okay, last time I pressed this twice.
So you included tropical storms in this calculation?
Yeah, the left-hand one was tropical storms. Yeah. There well, there's no information low on that. No one tracks them when they're below tropical storm force. If someone had tracked them, it'd be great. They track them afterwards, so we can track them afterwards, but beforehand, then no one tracks the things properly. I mean, they track the cyclone as it comes up to there, but you did for every tropical depression that becomes a tropical cyclone, there's 10 that don't. So you can't just say, well, I'm just going to take this little sample and say that's what it's about. It's the same problem with tropical lows. In our part of the world, which is a monsoonal system, tropical lows, I think, are a significant contributor as well. Show me a data set. Where that's actually considered so important that we're actually going ahead and starting to develop one to do it. Stop there, thank you. Okay. This is still on what makes it all happen. Vertical energy flux versus precipitation. Precipitation up here in millimeters an hour. Vertical flux in watts per meter squared. And remember, we call it flux, but it's actually conversion as well as flux is going on in there. And surprise, surprise, there's a big correlation. R squared is around 0.65. It has to be that because that's the only bit of energy that's in there that can be used. So it's not surprising that number is quite high. So you then come to the point of what makes the rainfall. And we'll come back to that in a second. This, just to show you the same thing, is the ratio of precipitation from tropical cyclones to total local precipitation around the globe. And I show that just as an offside to say that we're also not talking about small numbers. Those red areas are in the 40, 50, 60%. So those little transient tropical cyclones are actually putting an awful lot of water into the ground and a lot of energy into the atmosphere. Right, so what makes for efficient precipitation? There's a paper that actually explains this quite well, and if anyone wants it, I'll refer it to you, which Andreas and I wrote, along with several other authors, about a year or so ago, where we looked at convective and mesoscale convective systems. And basically, the really big definer of precipitation is the column relative humidity. Pretty well, nothing else matters. Column relative humidity, and you can see that result here. Column relative humidity goes up, precipitation goes up, and basically, it's pretty hard to get any reasonable amount of precipitation down here, which is one of the reasons that less than 26 degrees is bad for tropical cyclones. And then you get a quite steep climb. I don't think I'd put too much in this one dropping off. I think there's just so few data out there, but you get a quite steep climb up to about 80%. And the one on the right just shows you the tropical cyclones that went into that and the other diagrams I'm showing you. It's a weighted average. It's a mass weighted average, yeah. So if you've got 100% at 100 millibars, it doesn't make much difference. This is the vertical flux versus the column relative humidity, and you can see there's a pretty good relationship. So what's happened is the vertical flux is being driven or is being defined by the precipitation. There's a good relationship between this and precipitation. Therefore, there's a good relationship between column relative humidity and vertical motion. But there's another one that I'll come to in a second. Sea surface temperature, it's actually quite a poor relationship. And it just comes back again. I know I have focused way too much in the past on just sea surface temperature. In this particular case, higher sea surface temperature does tend to point towards higher column relative humidity, but not always. And as you can see here, it's a very noisy number. So if you use the area over which tropical cyclones occur, there's a relationship, and it's pretty bad. It's got an awful lot of scatter, and the degree of variance explained is actually quite low. The other one that comes out of this is if you look at the column relative humidity and then you go look at the tropical cyclone size, then if the column relative humidity is low, the cyclones are small. If it's high, the cyclones are big. Not our result. There's two references there. That's not our result. But the point here is that if the column relative humidity is high, you get more precipitation, more efficient precipitation, and you get a bigger cyclone. So you've got more of it going up. So you've got an add-on effect to the amount of energy that the cyclone can actually export to the rest of the world. So what we've said so far is we've got energy coming in the tropics into convective regions, but we're talking about the tropical cyclones. Up it goes, get a conversion, out it goes, and heads off into the never never. And tropical cyclones have provide around 50% of the vertical transport required to balance it, and there's this high dependency on column relative humidity. Just keep those in your head as we go on. We now come to this little one here, and the spatial and temporal transience of tropical cyclones and the large spatial scales everywhere they've got to go to be able to satisfy this component of the turn. And let's just jump right out of that and go look at a map. What we have shown here is the cloud optical thickness. The bright colors, the non-blue colors are clouds, and the blue colors are basically clear blue through purple colors are basically clear air. You notice something. Firstly, where the tropical convection is occurring is not where the moisture is coming off the water. I mean, this again is meteorology 101. If we had tropical cyclones in there in a very gross sense, here is where they go. These are the typical locations and paths of tropical cyclones. They're also not necessarily out in these clear areas, and especially the areas over the land. But those areas are cooling with radiation, and that cooling has got to be replaced. So somewhere or other, we've got to get this information around. And just to emphasize the area, the size again, that's a 5,000 kilometer distance, that particular arrow. So what we did, and this is new stuff, I think, yeah, this is the first time we presented this, is we actually went to the, this was just the ERA that I'm going to present. We've done it for the Japanese one as well. It's the same results. We took 36 parcels and released them every 6 hours at 100 meters above the ground, above the water, around the cyclone center. That gave, and then we did that over and over and over again for a number of tropical cyclones. That gave us 1,083 trajectories of 36 parcels, which so 36 times 1,083 actual parcel trajectories, which we ran for 720 hours, a full month, 30 days. There was a few constraints on it. After we released it, it actually had to at some point be advected above 300 millibars. It had to ascend through 500 millibars within the first 4 days. In other words, we didn't want to leave it there and have something else come along and sweep it up, and it got counted unnecessarily. And it had to descend below 500 millibars within the 31-day analysis. This does limit the process somewhat because there's a lot of parcels hadn't descended at that point, but all we're saying is, let's just look at what happens in that 30-day analysis. And I also have to say, it costs an enormous amount of bloody computer time to do what looks like a simple thing. These parcels are going everywhere, and just to simply do the calculations and everything else, it takes a while. Right, firstly, let's look at the sensitivity of starting height. We chose 100 meters. Look at the top diagrams for a second. And this is just from a selection of storms in this region. You can see that they're gone zippity-doo all over the place. The bars are actually a problem with the plotting system. When they go off there, it draws a bar across. 250 meters, sort of, they're different, but a little bit basically the same story. 350 meters, they're about the same again, except there's now a lot more of them getting into the subtropics. And across here we have the time section. So this is the top of call this 100 millibars, and this is the surface. They're all coming up and they're all drifting along, and they're coming down and they're coming down, and various other things along the way. You notice that quite a few of these would actually not have been counted because they didn't get back to 500 millibars in the time scale we're looking at. Same thing here and the same thing here. So basically, it's not all that sensitive to which level you pick to be able to get this to get a reasonable answer. If we then plot them all up, these are all the ones that were going up, and these are all the ones that were going down. And you can see the red is 240 parcels I think this was per year, yeah, per year coming up. And as you'd expect, they're where the tropical cyclones were. Remembering that they had to actually come down within the month as well. So all those ones are red areas are where they're going up. And the interesting thing is, and as far as I'm concerned, this proves the hypothesis completely. Look how they actually cover the entire globe. The tropical cyclones cover that small area. The parcels actually descend over the entire globe. And that's pretty well a random, almost uniform descent. There's a few holes in there, and I'll come back to that in a second. And if you like to look at it in this time scale, we're going from 0, 120, 240, 360, and then the full month over there. This is obviously the upward moving parcels. You can see how they, this is just the location of the parcel now. You can see how they spread out, spread out, spread out. And by a month, they're pretty well spread all over. The red numbers are higher than the numbers up there because this includes the ones that hadn't actually subsided at that point. Let's compare this diagram, or this map here, sorry, with the areas of outgoing long-wave radiation. So these are all clear zones where the outgoing long-wave radiation, the cooling is at its maximum, all the red ones. And then the bluish areas are where it's either lower or in most cases covered by clouds and things like that. And you can see that the parcels are actually subsiding preferentially in the radiatively clear areas. And it's not just that they're missing the equator. In this region they subside, and that's the only region where the radiatively clear area comes all the way across the equator, except for a little bit of an ITCZ. So basically there is quite a strong relationship here in the sense that the parcels have gone off, and they've preferentially gone into the clear areas, and then they've subsided in the clear areas. And it's not necessarily surprising, because if you're having subsidence here, which you have to have to balance the balance, then you've got a little thing called continuity, which says we'd like to have the mass come from somewhere. So if these things are wandering around, there's going to be a tendency to converge into those regions as well. I do have to say that when we first produced this, I just looked at it and said, no, it can't be that good, because that small area of tropical cyclones is really going over a very large area. And not only that, all the tropical cyclones that produced each of these parcels were dead. They were gone by the time you got to this point. Oh, wait a minute. I should have, did I have something else? No, that was it. Right. So to finish up the story for this particular part, and I'm going to be finishing a bit early because I really would like to get some discussion going on this. The timescales involved in what we're talking about is to bring, to actually evaporate and bring the moisture in here, and there is some sensible temperature transfer as well. coming into the cyclone area is a timescale which lasts longer than 30 days. Some has come in over just a couple of days, but lots have come in longer than 30 days. That's not new. I can show you papers in the 40s which said that. That's not new information at all. The timescale to go up here is hours, also not new information. The timescale to go out the top, which is new information, is that potential energy spreads off around the world on timescales which are also greater than 30 days. And then, whenever it's needed or wherever it's needed, we get the compensating GZ to CPT to compensate the subsidence, to compensate for 1 to 2 degrees C cooling per day. You got to drop about 50, maybe 100 millibars. I use millibars because it's compressional heating. So it's still, if this goes all the way down and keeps subsiding down to the bottom again to replace the radiative cooling all the way down the bottom, it would again take several days. But the large bulk of the radiative cooling is actually here up in the upper 300 or 400 millibars of the atmosphere. So that's where most of the action is actually occurring as far as these are concerned. And the last point I'll emphasize is that there is also a lot of local stuff happening here. I don't care about it. It's not important to me. But I'm definitely not saying you don't get local circulations happening in the process as well. It's just they're not important to this question. This has a fundamental statement about what is a very large body of work, actually, and this is not originally by me. I was about to present some of this at a meeting earlier this year at the Amos, and Christian Jacob came up and we were having a chat, and I mentioned it, and he says, "Oh, we've done a bit on that." He was looking at the convective radiative equilibrium, and if you go to all of the convective radiative equilibrium theories, the starting hypothesis is that that's satisfied vertically. In other words, you warm up the ocean, convection happens, it all gets sorted. Well, no. From what I'm just showing you there, it gets sorted over very large scales. And this was a convective radiative equilibrium study that Christian and a colleague and a student did, where they looked at the distance from where the actual, in other words, this is what you would call is where it all has to happen. And then you go and look at the distance, and you can see, you go out to the entire globe and there is still some of that adjustment occurring, even on a globe timescale. This was done on a world with no land, no horizontal, an aqua planet with no horizontal gradients and things like that, just to make it a nice simple process. Well, what I've just shown you is basically that, except we don't go to 90 degrees, we come out to about here or somewhere. And I think it does say something fundamental about that. It's not my work, I just wanted to mention it in passing because I think it is important. Right, near enough to the last slide. We've been looking at future tropical cyclones, and here we took the WRF run that we'd done for future, it wasn't actually done for tropical cyclones, it was done for weather over North America, but we took it all the way out over the Atlantic Ocean, as you do. And what we did was we ran WRF with current climate, and then we changed the boundary conditions alone to future climate. In other words, we let WRF sort it out in between. We did put the greenhouse gases in, so it actually includes the greenhouse gases in the Atlantic region, but it's the boundary conditions. And by doing that, it's not a real experiment, but what we're saying is if you change this bit according to what the climate model do, and you've got a high resolution model, this was done at 4 kilometers, what happens? And it was actually surprising. The boundary feeds transients and means.
So the transients come from future climate as well.
Well, at the boundary it does, but once you get into the center of the cyclone, the transients are all coming from what the models decide they should be. Yeah, but you do get, for example, easterly waves coming in the eastern side, and anything that goes back out, it just gets handed over and forget about it. So it's a one-way system in that sense. This is current climate. This was future climate. This was a 2-degree climate. There, the relationship between vertical energy flux and column relative humidity and the overall relationships around explain about 30 or 40% of the variance. It's correlation coefficient in the 60s. And you can see that this is current climate. This is future climate. And that's quite interesting because in the future climate, you actually end up getting a higher vertical energy flux. Sorry, a higher vertical energy flux at a lower column relative humidity. The cyclones are also slightly smaller in this particular run. So there's a little bit of a counterbalancing thing, but the end result when you work out the numbers are this dominates. So basically, as you go into, and sorry, the other thing that happens in the future climate is that the intensity of the top percentages, the top few, like the Cat 4 5s, if you like, but the top few tropical cyclones actually get more. They have more tropical cyclones in the top end and less in the bottom end. So that would have added to this as well. But if we just take this one, because we've actually, for some reason we don't understand, we've got more efficient convection out in future climate, possibly due to the higher surface temperature, who the hell knows at this point, then what happens is you have an explanation for why the IPCC and Kevin and many others have said you get a reducing number of tropical cyclones in future climate, not an increasing number of tropical cyclones in future climate. So I think this actually both supports that, provides possibly the first, it's certainly the first I know of, explanation for why they should be fewer. I've waved my hands in the past and said, well, they're more intense, therefore you don't need as many, you know, but it's waving your hands. This is the first objective information that I think we've got in this regard. It also has comment, it makes a comment about things like Kerry's little model that he actually, his pseudo-climate model, which he runs a two-dimensional model in a statistical dynamical sense inside the fields of global climate models, and he gets an increasing number of tropical cyclones. The reason for that is he's actually too sensitive to the sea surface temperature. So he's increasing them, and his model doesn't give a damn about the global energy budget. The big model's already satisfied that. So basically, I think that's the reason you get that increase in the numbers of tropical cyclones, and therefore I'd be quite careful about using the increasing numbers in Kerry's model as a sort of a good result or a result worth seriously considering. His intensities and other things I think are quite good, by the way. So let me summarize. Vertical transports, 50% of the energy. There's a dependence on cyclone intensity. There's also a much bigger dependence on column relative humidity. The balance is achieved by firstly shoving that up there where it can be used, but then the balance is achieved by the fact that the potential energy is exported to the globe, to the tropical globe, subtropical globe around. And I hadn't shown you the bits that go poleward in all of this. So remember, there's a whole bunch going poleward as well in this process. The next steps that we're going to do, we've already started breaking the results down into ENSO. We've already done them. We just need to break them down into the ENSO periods. We're trying to actually look at monsoon lows and things. We're actually doing other convective systems by putting boxes around the ITCZ to start with, because I want to get an objective number for this, which I can then compare with this as against comparing what people have said this is to what this is, using the same system. And this is going to be the one that finally nails it, because right now I've shown all of these things are important and the right dimension and the right scale to actually have a major impact on the radiation budget. I haven't actually shown you that the radiation budget depends on it. So we've just started the runs. We're actually varying the radiation budget. In other words, we're just changing the amount of outgoing long wave radiation. Well, not really, we're actually stopping the atmosphere cool as much as it should have. And we're going to make it so it cools less, we're going to make it so it cools more, et cetera, et cetera. It's going to be quite a bit of computing time, and it's going to take us a while to get there, but we've done enough in the start for me to say that there is a very large and significant impact on convection at large scales. And the interesting thing is, while all of this takes weeks, sorry, not months, well, and months, but weeks, days to weeks, the response, given I changed the outgoing long radiation or cooling, the response in the convection is like in a day or two. So what I think is happening, and we'll be able to document this once we got the models run, I think this is on an advective timescale. This responds on a gravity wave timescale. And I think that's a reasonable assumption to make because the balance does occur on a gravity wave style timescale. And that's basically it. Thank you very much for the invite.
Two microphones
Just reaching it past you here.
We have two microphones here for questions. Let me start with two small first questions. A, in your runs for the future climate, where you prescribe the greenhouse gases, CO2, methane, nitrous oxide.
We prescribe the greenhouse gases, which is obviously mostly CO2, but there is no, we only have greenhouse and methane. We don't have, well, we don't change the nitrous oxide type content. We just change those two. And we specify the sea surface temperature and we increase that to whatever the climate model said. It's a variable sea surface temperature, but whatever the climate model did, and whatever's coming in the sides is coming straight from the climate model.
And the CO2 and methane concentrations, do you assume them uniformly changing throughout the column, or?
Don't know. We put them in at about the sort of what the climate model actually had in it. In other words, we try and reproduce it closely. And I mean, don't put too much emphasis on the details in these things. This is like a bloody great fish saying, which way does it go? That's all I'm interested in. I don't like these pseudo climate runs, except they're very useful in this case because you can actually get rid of everything else and say, what happened if I get rid of everything else except for the important bits I'm interested in?
Yeah. My question was, I was wondering how sensitive it is to the vertical distribution of greenhouse gases. Like with methane, you won't have any increase in the above 100 hectopascal because it's all dropping off. With CO2, you only have a drop off of 0.5% or something. But how sensitive is?
We haven't tested that. No.
And the second,
if we do test it, I can assure you now, we'll only test it for regular convection. We're not going to run this whole thing 5 times for the entire period. It's a bloody expensive. I mean, this occupies much of the NCAR computer for like a month or two, just to do it properly, because we want it at high resolution. So go
on. Let's first give others a chance, and then I come back. Craig, and please introduce yourself briefly with the affiliation.
He doesn't need an introduction. There's no one left on Earth that doesn't know him.
Yeah, Craig Bishop, School of Earth Sciences, here at the University of Melbourne. Yeah, so I wanted to ask about, so you had the relative column humidity, and you're pointing out that, you know, when
the column relative humidity,
sorry, thank you. Column relative humidity. And you're pointing out that when the tropical cyclones are bigger, that's higher.
Yes, go on.
Yeah. I guess not that surprising, because once it gets big, you wonder, well, how the hell could dry air get in there anyway?
I should have said it. We're talking about the column relative humidity before the cyclone gets there.
Ah. Okay.
And that follows what the studies that did the same thing.
Okay, so there's a time lag.
Yeah.
All right. I'll hand on to somebody else then.
You have other questions?
Other questions?
Yeah, Greg, look, that was really interesting talk. I've got a specific question to ask you about the budget. The subsidence portion, would that potentially change in a changed climate and thereby provide an additional sort of correction to the budget that you might have to apply?
The answer is it almost certainly will. I mean, we all know that there is more rainfall in just general convection. If there's more rainfall in general convection, there is more energy being transported aloft. There is a greater amount of subsidence warming that can be occurring. We haven't got down to that level of detail, but yes, and I think it is important.
Sorry.
Yes.
When Craig gets to his second question, I charge a beer a question, so keep going, mate.
Yeah, so interesting. So suppose in future climate, the tropics arrange themselves, say that there was more vertical shear. And it was very difficult for a tropical cyclone to get going. Would that be, would that tend to cool the planet or warm it? Or, you know, we can go the other way as well. Suppose there's something in the large scale that gives us more tropical cyclones. Then can you just talk a bit about that?
Well,
so that's, I don't think we exactly know what's going to happen.
I don't know. Let's just simply make it easy and say, given something makes there more cyclones, then if there's more cyclones, they're going to have a bigger impact, which means that the tropical convection's got to die off. There is only so much energy wandering around in the low levels. So once you can petition it how you like. The tropical convection, at least from just a thought process point of view, has to die off a little bit to replace it. So the percentage would go up in the overall process. But I mean, the tropical cyclone and the tropical convection and nothing that's happening in the atmosphere, aside from gases and things like that, but nothing that's dynamic that's happening in the atmosphere is going to make any difference to the fact that the radiation budget's still cooling by 1 to 2 degrees a day. That's a driving force that is constant. And it doesn't change much in the future climate, by the way. It changes very little in the future climate. It's basically a very similar number. So basically, if we have more tropical cyclones, then something has to happen to the convection. If we have more convection, something has to happen to the tropical cyclone.
So it'll just redistribute.
Yeah,
is your guess?
Well, that's my thought process. Yeah,
right.
There's a long way between a thought process and an answer, mate.
Yeah.
So, yeah, I can sort of add a little bit to that because we've actually done some experiments where we've attempted to kill off all the tropical cyclones, and yeah, there's a balance between the rest of the tropical convection and the tropical cyclones. So it's
so you've seen it, okay?
Yeah, it's pretty much like you
definitely have a
said.
chat with you this afternoon then. Yeah. The big question to both of you, well, not question, the big unknown, which I am not going to answer. Well, when I say we, it's definitely a collaborative project, and it's Andreas that is a brilliant stuff between all the diagnostics. The big unanswered question is, why was it 80? Yeah. I don't bloody know. Well, no. All I'm telling you is why it's constant. And even when we started this, I said, I don't think we can actually say why is it 80? Because why don't you just have less tropical convection? I suspect if you change the arrangement of land masses and oceans, you get a different number. But why was it 80?
Hey, Greg here. One question for me. Just to clarify, so you said having stronger tropical cyclones, they don't contribute more to the vertical transport of energy?
They do. A more intense tropical cyclone contributes more, but not as much as the changes that we observe in the column relative humidity, that's all. It's about a 15% increase if you go from the weakest to the strongest.
So that then comes in line to the last climate change point where you said, okay, we have more intense tropical cyclones, and then in that would rather mean a decreasing number than a constant number, and if the energy transport would stay the same.
The climate, there's two answers from the climate point of view. There's what the models have been telling us, and they say, on average, I mean, some of them have got it going up, but the consensus viewpoint that total number of tropical cyclones is gradually going down. If you look at what's happened to now, and we've had a 1 degree warming, there's been no change whatsoever. In all of that, what's happened to now, there's been basically a doubling of the proportion of category 4 and 5 tropical cyclones, which means that there's fewer weaker cyclones. They've intensified better. They've had a better chance to get intensifying and things like that. And well, at least the paper we wrote, we said, well, it can't actually get to be much more higher percentage of intense tropical cyclones than that. So we've probably already had the future change now. You do a very easy back of the envelope calculation. Just drive a tropical cyclone, a random number of tropical cyclones through the Atlantic Ocean and say, okay, they can do what they like. They can all get to category 4, category 5. but they hit islands, they hit land, they hit all sorts of things along the way, so that you can't get them all up to that level. But coming back to the first question is that we've had a doubling of the most intense ones, and it hasn't made a noticeable difference to the way that cyclones partition energy backwards and forwards. There's no trend that we've seen, and at least in the last 25 years, sorry. Three beers.
Yeah, I was going to say, so you also did the experiment where you did the forced WRF with the future climate, and you found that the tropical cyclones were tended to be a bit smaller.
Yep.
Yeah. But you got more energy out for the same column relative humidity.
No, not for the same column. Oh, sorry,
right.
Yeah, for the same column relative humidity. Yes.
Yeah.
Yep.
Yeah. I was wondering, did you do the counterfactual experiment where you take WRF and you drive it with, as if there was no increase in CO2? Yeah, not use it, because it sounded like the way you described the experiment, you did one experiment where you kind of drove it with historical conditions.
That's correct.
And then you did another experiment where you drove it with future conditions based on a climate model. And I'm just thinking, the climate model
the
has
answer
lots
is yes.
of stuff that's different.
What I showed you here was the other one. We did run it where the horizontal boundary conditions in the dynamic sense were the same, but we did change the thermal boundary conditions to fit the future climate.
Oh, okay.
So we did do that one, made almost no difference.
Right, you did that one. But you didn't do the one where you just drove it with climate, but counterfactual.
No, we haven't done that one.
Yeah, okay.
In the interest of time, we are about to wrap up, but is anybody interested to inject herself into that ping pong match of the giants? Any more questions?
Hi, Andy Taylor. I'm actually from the Bureau of Meteorology. Part of your process, just as a high-level process thing, some of the diagnostics, you started with IB tracks and then put some particles in and watch where they go.
Yeah, well, we use IB tracks to give us the tropical cyclones. The particles go into the ERA interim or the Japanese reanalysis. But based on the cyclone being
based where
there.
the track was supposed to be. I was just wondering, is there any room for an inverted process where you start with particles everywhere and run them backwards to diagnose where the cyclone should have been?
Yeah.
Something along those lines.
If you talk to anyone that's tried to do trajectories, running them backwards across an atmosphere with very little in the way of gradients or anything like that will not only cause you nightmares. No, it's not. I don't. That's easy to do. We could do it, but I don't think it'd give us a sensible answer.
Wasn't even trying to give the answer. I was more asking. If you go one way, can you do is there any point going backwards? And especially because you're talking about. You could,
and if it's not too far away, but if the parcel was, say the parcel I picked was in the Atlantic and it happened to have come from a tropical cyclone in the West Pacific, there is an awful lot of other things you could do on the way back, and it doesn't take too much of a jiggle in the climate model to move it off to another grid. You saw the difference in just making a difference inside the cyclone by 100 meters or so made. I mean, so it gets to be quite difficult, I think, to do that. If someone else has done it, please step in, but I wouldn't try it, and it's also a very expensive exercise. So we are going to do going the right direction from the tropical convection. So I'll be able to tell you where the tropical convection went as well when we do that particular study. Well, we already started doing it, but yeah.
One final question then for me. The current state of knowledge in terms of intensity and the frequency of future tropical cyclones, and you touched upon it a number of times. If somebody would be as courageous and as successful to drag you back into the IPCC process for AR6, how would you write that summary statement?
Right now, I wouldn't change very much in the current IPCC, actually. Go back 10 years and we actually wrote papers changing it. because the IPCC didn't do a very good job of it early on. But what they've got there right now is pretty mature. And by pretty mature, I'm talking about the fact that the total number of tropical cyclones going down a little bit. There is, depending on which models you want to consult, you might get them going up a little bit in intensity. I don't see any taking it down intensity. The regions over which the cyclones affect is changing, but quite gradually. The latitude of maximum intensity, where the cyclone reaches its maximum intensity, has gone poleward. I think you've done some work in this one as well, haven't you? But it's gone poleward in observations by about 100 kilometres. And there's several of those sorts of things around, but that's sort of basically in the IPCC. I think the IPCC is about right now, to be quite honest. I'll pass over to you first, if you like, if you've got a question, but you've done a bit closer to it than me in the sense, by the way, I don't do IPCC. I've got better things to do than all that politics.
Yeah, I think that's fair. I mean, they're in the process, as you know, of formulating position statements and all of that sort of thing that is kind of preliminary to AR6 at the present time. And look, I think your summary is pretty much.
But you're in the group that I dropped out of, because when I retired, I wanted to give up things. That it was currently looking at the interim one. That's why I asked you the question. Tell us some secrets, dirty stuff.
I don't know. I mean, maybe we haven't quite finished the report actually.
Yeah.
But you know, in general, what you're saying is correct.
Yeah, right. Yeah.
He applies for another beer.
Oh yeah.
Okay. One more beer and then we will.
Jesus, folks, I'm going to have a headache tonight.
So the evidence for the increase in the proportion of intense cyclones, is that from the best track data, or can you remind me what experiments that comes from?
It's now from a whole bunch of different data sets. We did it from the best track data for the globe. We did it from from a landfalling tropical cyclone data set that we developed, which had was best track but also local information, and then from another landfalling tropical cyclone database that Roger at Pilkey at University of Colorado did. We also ran WRF and did a couple of, just on a couple obviously, but did a couple of testings of what happens if you do this and this and this, and it all showed the same thing. And we also used Jim, come on, Holland, it's getting too long. I need that beer. Yeah, he developed the satellite data set, a completely homogenized data set. And all of them showed the same thing. Yeah, obviously different results, slightly different results, but they all showed the same basic trend. Jim ran it on his new data set and he got a different result again, but I've been talking to him in the last couple of months, and he said, Jim Cosson, yeah. Basically it's getting the same thing. He just gets a lot lower than I got. Which using basically IB tracks and a couple of other things. So there's been a number of different ways of looking at it, but I think it's probably a solid result.
I was concerned about the homogeneity of the observational data set.
Mm-hmm.
5.
Yeah, but this only was used. I only used the period of good satellite observations. And as I said, Jim, it's a completely homogeneous. And the two landfalling ones were pretty close to completely homogeneous because they were actually developed by looking at what local information there was for landfalling cyclones as well. So there were 3 in there that were essentially homogeneous.
You have to watch that.
Yeah. Actually, an interesting thing that came out of that study was in the Atlantic. They actually over forecast intense hurricanes back in the 50s and the 60s. And so you've actually gone the other way in the Atlantic. If you just take the untouched data set and you go back into the aircraft reconnaissance days, it was because of the way they interpreted the sea state. They used to just look out the window literally and look at the sea state and said, you know, that's 75 knots or that's 150 knots. And I think there was probably a little bit of I got to apply a more stronger tropical cyclone than you type attitude going on as well.
Craig, thank you so
Thank you.
much.
Yeah.
We always strive in our seminars not to dumb it down for the general public, whatever topic we present, and you did a fabulous job in presenting the expertise at the forefront of the research. We're really grateful for that, and thank you also, Craig and Kevin, for the discussion. We have another expert next week coming on Tuesday, the 11th of December at 11 o'clock here, Pathways to an Economically Sustainable Hydrogen Industry in Australia. The expert is Sam Bruce from CSIRO, who do a lot of work in Australia on hydrogen. So please be our guests again next Tuesday. But thank you again for your seminar. Thank you. I was just trying in my climate modeling course to teach the students some of the energy balance. Fluxes,
Really well, use any of these you want as well, if you want. Yeah, no issue there. Yep, thank you. Yeah, yep.
And I just get the microphone.
Oh, yeah, I better not walk off with that, do I?
Before you
go to the toilet.